over here. And kind of like our red dwarfs will glow for a while after they're done fusing. So also these remnants glow for a while, planetary nebula glow for a while, but eventually they're just basically nebula out there that don't even glow. So in the center of that is actually a neutron star. So we need to talk about how do we know a neutron star is left behind, or how would we know a black hole is left behind? And so this is the slide again to show you how do you get a neutron star. Protons, electrons combine to give you a neutron, and actually they also release a subatomic particle, a neutrino. So the way we know that there is a neutron star is the presence of something called a pulsar. And a pulsar is, can be in different energies, and it was first detected in radio frequencies. So basically, and people got really excited because they were kind of scouring the Milky Way, and they came up with a radio signal that went beep, beep, beep. And so actually, this radio signal they thought might be like things trying to contact us, intelligent life trying to contact us. Because like, what does that, right? And so actually, they started with a prefix called LGM. And LGM, somebody has a great sense of humor because LGM stands for Little Green Men. So we had LGM source 1, okay, and then they looked and they found another LGM2, LGM3, LGM4, okay, and then as it turns out, these are actually just like little blips from a neutron star. Okay, so how do neutron stars give you these little blips? Okay, well, we'll talk about that in the next slide. But this is actually, again, showing you the blip. Now, I kind of went like this, but they're a lot faster than that, because actually this is showing you in visible energies blips that are only, 0.033 seconds apart. So, and they're actually, this is that supernova remnant. This is actually called the Crab Nebula. It's a supernova remnant. And it is actually Messier object number 1. I guess it's the first one he saw. So that's M1. So how do you get like those little blips we call pulsars from a neutron star? Well, down here is a neutron star, okay? And notice that this little stick thing right here is its axis of rotation. So that right there is what it's spinning on, okay? And also notice kind of these ghosty looking magnetic fields. We've kind of seen Earth has a magnetic field, okay? This neutron star ended up with a magnetic field. So as it turns out, in this case, the magnetic field is going in a direction other than what it's spinning, okay? So with that in mind, actually those little blips, the pulsar ends up being kind of, and we kind of liken it to a lighthouse. So it's spinning, but it's kind of got a signal that's going kind of cattywampus from how it's spinning. So it basically kind of makes kind of a coning. So like if my hand is the pulsar, you guys would see blip, 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 like that. And that's kind of, and its axis of rotation is right here. Okay, so anyway, pulsars are from neutron stars. But, and how do we know that there's not some other object kind of spinning that actually has this kind of tube of energy coming out associated with its magnetic field? Well, we look at we can get to the mass of the object, we know the volume of the object, and that sort of situation, it needs to be a neutron star. All right. So, we're still not done. So, neutron star, picture this. Instead of a white dwarf, picture a neutron star. Okay, I know this looks like, okay. So, I'm going to put ND for neutron star over here. Or, sorry, WD. I'm going to put no I'm not. That was a white dwarf. I'm going to put neutron star right here. Okay, what is a neutron star? Basically, a massive star lived its life, it blew up, and what was left behind was not a black hole but a neutron star. Notice it's got a companion, which now as I'm talking, why didn't the companion get blown up? Are you like me? Are you with me on that? Okay.
Because it was made after the supernova? The redness?
Usually companions or binary stars are made at the same time. I guess I'm kind of thinking that the shock from the explosive supernova event wasn't enough to blow up the star next to it. I'm going to stick with that. Because we know this happens. So we said that that disk of material around the white dwarf was an accretion disk, okay? And actually see the word accreting. So basically it's still an accretion disk, okay, around this neutron star, okay, as matter from the probably swollen red giant comes. And then we also said that the matter in the accretion disk earlier heats up, so the matter in this accretion disk also heats up. But actually, there's even more thermal energy created here, such that we can not only just see like heat, infrared radiation, but we can clearly see X-ray bursts of X-rays, okay, that happen as basically nuclear fusion kind of sets in. So this accretion disk is even more crazy awesome than the accretion disk around the white dwarf in the companion. So those, if you run into the term X-ray bursts, there you go. There's a source for X-ray bursts. Okay, so neutron stars have a top mass, just kind of like white dwarfs. Remember, white dwarfs had the top mass of 1.4 solar masses. Neutron stars can't be any bigger than 3 solar masses, or something happens. Basically, if they're more massive than 3 solar masses, then the neutrons can't support the mass, and you're going to get a black hole. And let's see, what was that? I think it might be 25 solar masses, maybe, as a main sequence star that gives you this remnant that ends up giving you the, yeah, there it is. So I have another thing to put up here. So we have high mass stars greater than 8 solar masses, and then we have high mass stars that are 25 solar masses or greater. So 25 solar masses or greater. Okay, these will give you, BH stands for
Black hole.
black hole, yep. And these will give you, and S stands for
Neutron star.
neutron star, exactly. So that's kind of what we got going on there. Very good. So let's talk black holes. Probably I'm going to pull in, when we go to the next unit of material, we're going to need to talk more about black holes. And I'll probably bring in an expert on a video or something. But black holes. Well, first off, we talked about one way you get a black hole. Basically a massive star, okay, more massive than 25 solar masses as a main sequence star. It goes supernova, and the thing that's left is a black hole. That's called a stellar black hole. But honestly, you can get black holes in a lot of different ways. The only criteria to get a black hole, basically, is to take normal matter, and basically you've compressed it, so you've turned it into neutron soup, right? And then you try to compress it more, and it won't. So basically, it forms what we call a singularity, okay? Which is, I still think it's like a tear in the fabric of space and time. I still think, and I'll show you the image I think of. Okay. I guess it's coming up here in a minute. The other ways, sorry, I didn't say that. So the other main ways, actually in the center of galaxies, remember we said our Milky Way galaxy has a black hole in the center of it. We call that a supermassive black hole. Also, we think that there are black holes that were created like at the beginning of the universe, the time of the Big Bang. So those are kind of the different ways black holes are created. So this actually is what I think of kind of as a hole in the fabric of space and time. So Einstein, and the library actually has a book, Einstein for Dummies. So Einstein came up with several theories, and among them, he talked about the fabric of space and time. So basically, he said the heavier an object is, okay, it actually rests on the fabric of space and time. And that's what that gray kind of sheet is. And as it rests on there, it creates kind of a little dent. And that gravity actually, why would an object be drawn toward, why would something be drawn toward another object? It's kind of falling in because of the fabric of space and time is bent. So if you get an object that's dense enough, it basically makes a hole through the fabric of space and time. So like the video said, black holes are called black because no light can escape their vicinity. And I have an equation coming up. How do you calculate how fast something needs to be going in order to escape the gravitational pull of another object? And that's kind of why light can't escape. It's just not going fast enough. There it is. So I think clear back in Unit 4, Unit 5, we talked about the escape velocity of the Earth, and we said something needs to be going like 11 meters per second or something. If you want to leave Earth's gravity, you have a minimum speed you need to be going in order to escape the gravity of the Earth. That's called the escape velocity. So the deal is that you can calculate the escape velocity from any object, okay, of a certain mass. M is mass of the object you're trying to leave. Okay, G is a constant. The other variable is R, and R is radius. Okay, radius of, and so the way you look at that is this is a planet. Okay, we'll call that Earth. Here's the center of the Earth, and here's a person up here. Okay, so basically you need the mass of the Earth, okay, and then you need the radius is how far away you are from the center of the gravity. So for us, that would be our R term. But see how this works is if you increase mass, then you increase escape velocity. That makes sense. But do you see this where if you reduce the radius, that's what you're dividing by, you also increase escape velocity. That's exactly what we're doing when we take an object that, let's call it a white dwarf, and then a neutron star, and then a black hole. Basically, we're decreasing the radius, the distance between where you are and you want to leave, and the center of the mass. So that means that actually you can turn anything into a black hole. We talked in my other class about a pet black hole. So why not? Okay, you could turn anything into a black hole. You just need to basically take the matter and squish it down enough. So the example here is if you were to take Earth, okay, take the Earth with our mass, and the mass would keep our mass, keep that top term, but make our radius that, which is kind of strange, basically from the center of the Earth out to the surface of the Earth is 1 centimeter, which is really weird. Okay, I know we wouldn't all fit on that, right? Okay, but at that point, basically, we have created a black hole. What's a black hole? Basically, the escape velocity is faster than the speed of light. That's it. That's a black hole. All right. So the anatomy of a black hole kind of looks like this. The surface of the black hole, and I'll kind of do a drawing here at the bottom, I think. The surface of the black hole, the edge of the black hole is called the event horizon. And that's kind of like you kind of go back and forth between the event horizon. Like if you're close to the black hole, you're doomed. You know, if you're on the other side of the event horizon, you have a fighting chance. That sort of thing. Then the distance between the center and the event horizon is actually called the Schwarzschild radius. And the larger the mass of your black hole, than the larger the event horizon. That makes sense. So black holes only warp space and time in the vicinity of their event horizon. So if you're on the inside of the event horizon, you can't escape because you can't go faster than the speed of light. You go faster than the speed of light, we might be talking. Okay. And Einstein describes why nothing can go faster than the speed of light. Makes you want to go faster than the speed of light. Wait a minute, Star Trek, don't they go faster than the speed of light? They don't? Okay. Is that warp? No? Okay.
It's not faster than the speed of light, though.
Good. I'm glad to hear that. Okay. So you might be thinking, okay, so if something falls into the black hole, what happens to its stuff? Well, we already kind of said in a neutron star, basically your protons and electrons combine to make neutrons. Well, what happens to the stuff that falls into a black hole? Well, it's even worse. It's basically subparticle soup. So one thing, again, back to the anatomy that I didn't say yet, is that singularity point. So I'll kind of draw it down here right quick. So the anatomy looks like this. This point in the middle is singularity. Okay, and then I could do a dot, 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 and that actually would be the event horizon. That's my event horizon. And then actually I could go from my singularity out to the edge of my event horizon. Okay, and that is my Schwarzschild radius. So that's kind of how that works.
Is it just a disc or is it like spherical?
That's what I think it's not like two dimensions. It has to be, to me, like more, is that kind of what you're saying?
Mm.
Yeah, I agree. I think it has to be from all directions. Although these were formed by, these definitely had a plane about them because the star that formed, these stellar black holes were formed from something rotating in it. So I don't know. I agree though. It hurts my brain to think about it. I think so. So there are videos out there that address this. So what if our sun, not the Earth, but what if the sun shrank so that it actually could become a black hole? It wouldn't have to be bigger than 1 centimeter in radius. Only if you're near the event horizon would anything change for you. So actually, here's a little picture to kind of show you that if the sun were, well, maybe it's not showing you, but if the sun were to become a black hole, we would basically continue about our business. Okay, the event horizon would not go out to us. But this is showing you what Einstein said, that all objects create even us. We're walking around on the fabric of space and time. We're creating little dents. Okay? And that's actually why gravity works the way it does. Kind of reminds me of one of those things like when you, maybe it says down here, when you go shopping where like you can give a donation and the little coin goes round and round and round and round. Yeah. You know. All right. So falling into a black hole, and I can't remember if the video talked about this or not. I still think we're going to watch a documentary on black holes. So this figure actually has, I have a few things to say about this figure. First off, you are in this spaceship here where it says 50, okay? You are in that spaceship, okay? And this says that actually we are orbiting a black hole that is 10 solar masses, okay? And we are going to, we're on the blue clock, and we are going to send an unmanned spacecraft towards the black hole. So we are on the outside of the event horizon, so we're okay. Okay, we're on the outside of the event horizon. We are going to send, actually the event horizon, I think for purpose of this, is think where it's black, I mean, that's the event horizon on the outside of that black thing. So we're going to send our unmanned spacecraft, which also has a blue clock, towards the black hole. Okay, so you already see it's red. That's actually one of the things that happens as, in this case, the spaceship gets close to something that's very massive. and very dense. That the redness actually is called gravitational redshift. The way I think of it is that this ship that we sent closer to the black hole is sending us information from this red clock. And in order for that information to get to us, it has to climb out of kind of what I call a gravity well. I know I've heard that. I don't know if it's a science fiction show or not. But kind of out of gravity well, and it loses some of its energy. So instead of being blue, it's red. It's called a redshift. And we can actually see that not just with black holes, but with neutron stars and white dwarfs. Okay, white dwarfs. Something else happens. Can you see, not only is it red, but the time is different? Check this out. Okay, so we have 50 seconds, for instance, lap on us. We have only 15 seconds lapse for that clock. Now, the clock is not malfunctioning. Time is, from our perspective, looking at that perspective, time is unfolding more slowly. Time is ticking more slowly right here than it is here. Is that not weird or what? It's called time dilation. There's different ways to get time dilation. This one actually is the influence of gravity. Another way you can get time dilation is to go very fast. Okay, so have you ever heard the thing where if, there's twins and one goes off on a spaceship and it's going like half the speed of light, for 20 years, he comes back and going fast like that, time slowed down for him. So he comes back and he sees his twin and he's like, oh my gosh, you really have aged. And it's like, yeah, he didn't. Okay, so it's the same thing. It's called time dilation. Is that not cool or what? We have seen this, by the way, before I move on. Time dilation. Oh my gosh. So like jet airplanes, right? Go pretty fast, not the speed of light or anything like that. But actually, they can and they have put a clock, an atomic clock, which is very precise, in the jet plane, okay? And actually then compare it to another clock that doesn't move, and this one ticks off less time. Time unfolds more slowly in that frame of reference. That is so cool.
I was in Donald Trump's private jet the other day because I work at the airport in Burlington, and he was there, and I was talking to the pilot, and he was like, yeah, we can get from, because they came from New York to Burlington, but he's like, we can get from New York to Los Angeles within an hour in his jet.
Wow.
Yeah.
That's booking.
Yeah. It's like one of the fastest jets.
No
Did you
speeding
see Donald
tickets.
Trump?
Yeah, I got a selfie with him.
Did you tell him that his hair was stupid?
No, he was really rude.
He was really rude?
Yeah.
That doesn't surprise
He
me
was
at
really
all.
rude.
Yeah.
And he's changing his hair too, but
He is changing his hair?
I think so. It's less orange.
Yeah, it was like blonde.
Well, there's no way it's real. So I guess, let's be honest here.
I think it is.
I don't. I really don't think that's real hair.
It's real.
You don't think it's real either?
It's real.
Oh.
It's a toupee.
Anyway, that's it. Oh, goodness. Okay. All right. So is it, how are we doing? What's after this? Is there any more slides after that?
That's
Cool.
it.
All right, we're doing good. So there is this thing called spaghettification, right? And I'll tell you what it is. I'm leading up to that. But now let's switch scenarios, and basically you have a colleague or, let's see, consider or spacecraft decides to see, all right, so someone is going to enter the black hole. That's sad. And I have a picture here. That is the person entering the black hole. It's like, oh, that can't be good. So you see here where his feet are being pulled toward the black hole. Here's the event horizon, so here's singularity down here, okay? And his, yeah.
That doesn't look very comfortable.
It does not. And I've heard it described that actually this pole, I'll put it like this pole is way, way more than even this pole because of how close it is to singularity. This is singularity. So my point is basically it's kind of you're stretched like that. And Neil deGrasse Tyson does a little blurb on this, and he calls that like cosmic yoga. It's like At first it feels good, he says. Then not so much, okay? So, yeah. So you don't go in, but your colleague does. Colleague takes plunge. And so it's like we saw with the spacecraft. The deal is he will change colors, okay? Whatever color he is, he'll be longer wavelengths, okay? Redshift will occur. And also it'll look like he's slowing down because his time goes slower and slower. His time goes slower and slower. And I've heard it described, and I can't quite follow this, that you will never really see him go past the event horizon because his time will appear to basically stop to you because it's going so slow. Okay, now that's just from your perspective. The thing about him is
He's way gone.
he's way gone, yeah. His time did not stop, okay? So that's kind of, I've heard that described like that. So he seems to hover the event horizon. His watch stops from your perspective, and it seems like to take forever. Can't you just die? For him to cross the black hole from your perspective, not from his, okay? From his, it probably goes very fast, okay? He would feel like he's going faster and faster, like acceleration due to the force gravity, okay? And he would pass the event horizon, okay, and his atoms would be turned into subatomic soup, basically, okay? And he would just basically, his mass then would be added to the current mass of the black hole. And so here's where Neil deGrasse Tyson, I don't know if he came up with this or not, but he said there's different ways to like lose your life. You know, there's you can die by electrocution, you can die by suffocation, you can die by all these different ways. Now here's another way. It's called spaghettification, and it comes from the fact that basically you are extruded into basically a stream of atoms.
Turned into
subatomic
spaghetti.
particles. Yeah, you are. So, okay, so we know that neutron stars are there because of pulsars, okay, and we know that, well, this is a way then to know how black holes are present. That's right. And this is my own analogy. It's like you cannot see a black hole, but you can see it influence other things. We'll talk a little bit more about how we can see black holes in the far reaches of our universe. And it's kind of like when you go fishing and you have a bobber. You can fish on, whether you're fishing with a weight on the bottom or if you're fishing with a bobber on the top. I mean, either way, you do not see the fish. Okay, all you do is you see the bobber move or you see the pole go like that. Okay, and you try to figure out how to catch your fish. Okay. It's the same thing with things in astronomy, including black holes. We've seen the influence of black holes only if, as far as I know, they have a companion. Not just any companion, but the companion has to be close enough to dump on it, right? A close binary companion. So we did a little bit with constellations. Is the Northern Cross. Okay, this is the head of the cross, this is the foot of the cross. It's also called Cygnus the Swan, where actually the top of the swan is here, okay, and here are the arms, okay. Well, my point is there actually is such a situation. There's a regular star that we can see and then it actually has kind of an X-ray emitting, because that's what the accretion disk emits. Here's the accretion disk emitting X-rays. And we see this companion. There's no star there, okay? And we can actually deduce that that is a black hole. So, like on the GO2 telescope, you can actually tell it what you want to see. And on the menu is, do you want to see black holes? I think I might have told you that. I just think that's so funny. Why would I want to see a black hole from my telescope? So, anyway, somebody get a kick out of that. Okay. So when we talked about different types of energies, way long time ago, it seems like forever, okay, we said that it goes visible light, and then it goes ultraviolet, and then it goes X-rays, and then it goes gamma rays. Okay? So gamma rays are very energetic energies, and actually we think that gamma rays are also an indication of the presence of black holes. Okay. So we think that, or they think that, actually gamma ray bursts might be generated as a star blows up. Supernova type 2, that was our massive star blowing up, supernova, and a black hole is formed. Okay? That was the last slide. Very good. Okay, so we'll take a short